Okay, folks, here's problem 415. Very similar to what we just looked at in 411 with the condominium complex. This one is a town is thinking about building a new community center for a variety of different activities. And what they have come up with at this point is the options for building the center: a small center, a medium center, a large center. And then they have a demand scenario for the center, a worst case, a base case, and a best case with associated probabilities. So you can read through the problem to set this up. The first thing we need to do in part A, very similar to what we did in 411, is first thing you're going to do is compute the expected value of each of the three options. And you will note that the medium and the large both have an expected value of $605,000. So at this point, those two options are in play. Part B asks for the risk profiles, and effectively all you're doing is taking the, in this case, you're taking, or for the best options, the medium and the large options, and you're basically showing them visually. So if you notice that the net cash flow here is 0, minus 250 corresponds to a probability of 0.1, 650, which is about here, corresponds to a probability of 0.6, and then $800,000 corresponds to a probability of 0.3. So this is for the medium. This is the large. You can take a look at that. Compute the expected value of perfect information. So the expected value of perfect information, as you saw in the book, the computation for that is the absolute value of the expected value with perfect information minus the expected value without perfect information. So remember, there are three scenarios here: the worst case, the base case, and the best case. If I go up and I look at the payoffs in each one of these categories, worst, base, and best, notice that the best outcome in the worst case outcome is $400,000. The best outcome in the base case is $650,000. And the best outcome in the best case scenario is $990,000. So with those associated probabilities, if I had perfect information on which size facility to build, the expected value of that decision would be about $727,000. And that's using the existing probabilities for each one of the demand scenarios. The values that we computed up here are the expected value without perfect information. That's just, again, we went through an expected value of each of the each of the scenarios with the dollars projected. So the expected value of perfect information here is, again, the difference between the EVWPI and the EVWOPI, which gives us a value of about $122,000. And it explains down here to say, hey, if you wanted to go spend a little bit more money to do some research, that research would be worth up to about $122,000 to try to raise the probability of getting a little bit closer to this calculation where you have perfect information. Part D is it's basically a repeat of Part A. I'll let you read that. You just need to go back, compute some expected value probabilities or expected values. You can use this chart up here if you want to do that, because again, I will give you this spreadsheet. The last case here, or last thing here to consider, the consultant has suggested an expenditure of $150,000 on a promotional campaign over the planning horizon will effectively reduce the probability of the worst case scenario to 0. If the campaign can be expected to also increase the probability of the best case scenario to 0.4, is it a good investment? So what you'll see here, and I'll leave you the discussion, I just went back and again, I just recomputed the expected value of each, changing the probabilities of the worst case and the best case, and you can see what the expected values are. Let's see, I think that that will just about do it. Yeah, that should do it for this one. So again, this is just a little bit more on the expected value side. What we did add in here, again, this idea of a risk profile and the computations for expected value of perfect information. You'll probably see those again You'll see those again in some of these other problems. Excuse me. So let me. So why I want to save a little bit more time. Problem 4-5. If you've gone through the homework yet, it's obviously it's never a bad time to talk about football. So we're going to talk about football here. This question is basically saying if you know about American football, you know that after you score a touchdown at any level now, you can kick the extra point or you can go for 2 points. And basically what we're saying here is Temple is down by 14 points. And assuming that they can hold their opponent, let's see, Killeen Tigers, if they can hold them to no scores, what is the best option after their first touchdown to either go for 2 points or kick the extra point and try to win this football game? And so there's some assumptions here. There's an assumption off the bat that the probability, I want to make sure I see it here. Yeah, I think what I use, well, so let me just set it up there. And I use something a little bit different. This is one I took out of somebody else's problem, but I have done this with my assumptions, and I've got them right here. Let me just highlight these for you and make sure you know what I'm saying here in my decision table here. The probability of success, meaning the probability of success of making a 2-point conversion, is 0.4. So it means the probability of not converting the 2-point conversion is 0.6. And notice that there'll be some options here that these games go into overtime. And then so what the assumption is here, and this is a little bit different from what's on the example, but this is what I'm using from my numbers. The probability of winning in overtime is 0.5, and the probability of losing in overtime is also 0.5. Let's see, if you go back here in the question, so we're going to set up this. I think this table in your homework is actually going to be set up. The first thing that you're going to do is you're going to go through and fill in these tags for you're either going to win the game or you're going to lose the game, based on the decisions and the outcomes. And then over here it says for part B, assume that a win results in a value of 1 and lose results in a value of 0. Further assume that the probability of converting a 2-pointer, yes, that's where I put mine, is 0.4. Should Temple's coach go for a 1-point or 2-point conversion after scoring the first touchdown? So again, I think you're going to see this decision tree in your homework. What I have done is I have replicated it over here. I wanted to put some color to this to point out a couple things and just kind of walk through this a little bit to see how you can answer part B. So first of all, notice that my tree lines with theirs, but notice I've got some cells that are black highlights with, I think that's a yellow, those are yellow numbers in there. Each one of those are places where you are going to have to make a decision. And then the decisions, the outcomes of those decisions play out in the information to the right of each decision. So this decision plays out here, this decision plays out here, this decision plays out here, and this decision plays out here, so on and so forth. And again, you kind of glean that from the reading. Notice what I have done is I've gone through and based on my table here, I have shown where options lead to winning and where options lead to losing. And notice in the wins, or for the wins, I have labeled them win 1, win 2, win 3, win 4, win 5, and win 6. And that will kind of help me just kind of talk through some of the calculations here. So what you're going to have to do in order to answer this question is notice that I have listed all of the nodes here. I've got, let's see, I've got 11 of them. Actually, I didn't write it here, but I'll show you how we get the answer for node 1 here over in this little chart that I've put together. And so what you're going to have to do, a lot of this is expected value. It's a lot of and or calculations, if you remember from probability. So basic ideas in that regard. So what I'm going to do, again, I'm going to take this tree diagram or decision tree, and I'm going to work backwards. And the 2 key nodes that I'm going to use to make my decision here are basically going to be node 2 and node 5. And so remember, if we start over here on the left, remember, so the Temple's down by 14 points and they score a touchdown. So the question here, the first decision that you need to make is, are you going to go for 1 point? Are you going to kick the extra point, or are you going to go for 2? And remember, it says in the reading that if you're going to kick the extra point, the extra points are automatic. There's nothing to be concerned about there. If you say, hey, I'm going to go for 1, then you're automatically going to get a point. So let me just go through this since I've started here. So if I kick the extra point, the next step is, well, I've just scored another touchdown, and what am I going to do now? Am I going to go for 2, or am I going to go for 1? If I go for 1, I will make that, which means the game is tied, and then I'll have to go to the next step and play in overtime, and the probability of me winning in overtime, remember, is 0.5, and the probability of losing in overtime is also 0.5. So if you go to node 9, the calculation here is 1 point for winning times cell 0 or 09, which is the probability of winning in overtime, plus 0 points times the value in cell 010, which is also 0.5. So the expected value for node 9 is 0.5. If I decide to go for 2, the probability of success is is 0.4, right? 0.4 here, and the probability of success of losing here is 0.5, but it's a 0. So the outcome, or the expected value for node 8, again, is going to be 0.4. And again, that comes from if I convert the 2-point conversion. Remember, I scored 1 point here, and if I score 2 points here, that means I win the game by 1 point. So the expected value of node 8, again, one more time here, is 1 point times the probability of success in overtime plus 0 times the probability of failure in overtime. So what I've done with that basic idea, that is the same question or the same approach that you have to take over on this side as well. What I have done, let me just say to close up the video here, and then you all can get on with the computations. Remember, I said, once you go through and compute all of your expected values at each node, and if you just go through the calculations that I show in my sheet, you can use that to guide you. You certainly should take a swing at this first by yourself, and then if you need to look at what I have done here, you can certainly do that. The final step is to go through this scenario here, where you look at on each possible leg of the decision tree or branch of the decision tree, where you can win. So, for example, you can go for 2, be successful, kick the extra point, and you win. And the probability of that is 0.4. So I do the same for win 2, win 3, win 4, win 5, and win 6. Notice here, to come up with the expected value of node 2, you're going to have to add together a couple pieces, and I explain that here. But I think that this is certainly enough to get you going. And like I said, when you look at your own algorithmic setup here, don't be bashful about taking a look at my sheet here and looking at how I computed these probabilities, and that should be helpful. So again, any questions, let me know, and let's get off to a great week this week. Thanks again for joining me.